Hello and welcome to week 5 of Neon Dev Bootcamp. This week we are going to learn how to interact with Solana's Raydium protocol directly from your Solidity contracts using Neon EVM composability libraries created specifically for Raydium interaction. So if you've ever shipped a dApp on Ethereum, chances are you've touched Uniswap, whether it's V2, V3 or routing swaps under the hood. You've probably seen this DeFi protocol. But what happens when you take the same DeFi logic and push it to a radically different runtime environment like Solana? That's where you need Raydium. Raydium is a flagship DEX on Solana with all the familiar DeFi concepts, but very different implementation details. Just like Aave and Uniswap are separate from Ethereum Foundation, Raydium is an independent DeFi protocol on Solana, not maintained by the Solana Foundation itself. What are the differences and what are similarities between Uniswap and Raydium? Well, first of all, both Uniswap and Raydium offer automated market making. They offer pool creation, liquidity management, and swap logic with slippage control, as well as LP token handling. But the dev experience and architecture differs massively between the two. By the way, did you hear that Uniswap logo was inspired by the famous medieval unicorn tapestries at the cloisters? I've heard it in the podcast and just wanted to share it with you because I find this detail very beautiful. So sorry for derailing a bit. Yeah, so these medieval unicorns look kind of like that. I think they're great. Anyway, back to the differences between Uniswap and Raydium. If we look at the execution environment, with Uniswap, everything lives in the EVM. You deploy contracts, define your tokens, and interact through Solidity with static calls. But Raydium is built for the Solana runtime. And programs are stateless, instructions are passed explicitly, account management is manual and also explicit, unless you're using a helper library like we will today. Because our helper library for Raydium interaction abstracts away all these difficulties. Now, if we look at the pool logic, in Uniswap v3, it's concentrated liquidity and custom ranges, and it makes sense to compare the Raydium SPMM pools to Uniswap v3 because they both handle concentrated liquidity. And Raydium CPMM also have config files which define the behaviors, ranges, and fees, unlike Uniswap, but we'll look at that a bit later. So the key difference is that Uniswap pools are typically 3-5 accounts, but Raydium pool creation can involve 20 plus dynamically derived accounts, especially when locking liquidity or using NFTs. So now let's go and have a look at the Raydium program library created by Neon EVM. From this library, you're going to be able to create Solana native Raydium pools, add, remove liquidity, lock LP positions as NFTs, trigger swaps with swap input and swap output, and collect the fees. So we are going to be focusing specifically on CPMM pools, Raydium's concentrated liquidity pools, which allow LPs to define custom price ranges and optimize returns. We've actually used this library already to create our meme coin launchpad a couple of weeks ago. So back then, we took a pragmatic approach and simply replicated the logic from this library. But now we're gonna dig deep and see what's in it so that you can use it in any DeFi project you'd like. Now let's have a look at the instructions. For example, here in this library, we have 7 instructions. Create pool instruction, obviously for deploying CPMM pool on Raydium for a selected token pair, token A and token B. Then we have an add liquidity instruction, which is adding the liquidity for the selected token pair. Then we have a withdraw liquidity instruction, lock liquidity instruction, which locks the liquidity and gives you an NFT position for the locked liquidity, and then collect fees instruction, So when we have some traffic in the pool, we are going to be able to collect our fees, and then swap input and swap output instructions, which are basically a reversed instruction. The input specifies how much tokens you have for X amount of tokens you're going to receive, and swap output instruction specifies how much tokens you want to receive. For example, you want to receive 100 tokens and you don't have the exact amounts which you're gonna input to receive 100 tokens. Is gonna depend on slippage. Anyway, we are gonna go into detail of swaps a bit later. So each of these instructions is described in detail in this library. What parameters you need to pass and what exactly those parameters mean, but we'll concentrate mainly on how to call these instructions from a Solidity contract based on this contract sample called Raydium program. So first instruction is create pool instruction. Here you select a token A and a token B, mint amount of tokens provided as initial liquidity provided to the pool, and starting time of the pool. We define token mints for both tokens, and we find the associated token accounts for the contract which is going to create the pool. Then we transfer the tokens from the user to the ATAs of the contract. And from here, the contract has permission to initiate composability request in the context of Solana. Now there is something new here which we haven't seen before. It's called pre-made accounts, and these are accounts that we need to optimize instruction building and spend less for gas. So we need basically these accounts to take the tokens from the user, but then the Raydium program also needs these associate token accounts, and to not calculate them again and pay for these external requests, we have this array in the library to use the list of pre-made, pre-calculated Solana accounts for simple optimization. So we just pass these pre-made associate token accounts to the function, and there is a check in the library where we generate 20 accounts needed for the pool creation. And basically this checks if we pass a pre-made account, and if we don't, it's going to generate a new ATA, so create this external request, which is going to cost us more gas. And that's why we need to pass these pre-made accounts here. Then we create a pool instruction and execute it here. At the end, we return account with index 3, which is actually a pool ID. You can see it here. And the pool ID can be calculated in the Raydium data library by the method called getCPMM PDA pool ID with the config account, token A and token B. And here we also specify the config file. There are several configs available to choose from on Raydium. They have different conditions for pool creation, and our library uses the first config, which requires to pay 1 sol for pool creation. But you can check other configs and play around with them to see what kind of behavior they allow. So here is our config index that we are passing to the create pool instruction. It says it's 0, which means that it's the first config from the list. Now, next instruction is add liquidity instruction. When you create a pool, anyone, both you as the creator and others, can use this instruction to provide liquidity to the pool. We define the pool ID, input amount for both tokens in the pool. Then, with the base-in boolean, we define if token A or token B should be used for the LP amount calculation. We define slippage, a very important parameter which you'll have to think through, because, for example, if you put the maximum 100% slippage, you're open to sandwich attacks. And I'd use, for example, 1 or 5% slippage. But depending on your use case, you might want to decide to raise the slippage percentage a bit. Some people use even up to 50%, but I mean, it really depends on the use case. Also, we have return data and pre-made accounts. All the instructions have these parameters, return data and pre-made accounts, and most of the times the return data boolean is true. You want the instruction to also include the instruction data. If it's false, we'll return this data as empty. And later I'm going to show you when we need to return this data as empty as well. So let's go to the implementation. Here we define pool ID, and we deployed it in the previous instruction. Token A, token B are their amounts, input amount, and the slippage. Then we calculate the associate token account and the token mint. Then we make the transfer and we pass the pre-made accounts for optimization. Then we build the adding of liquidity instruction and we execute it. Now, next instruction, we withdraw liquidity from selected token pair. So again, we pass the pool ID, the LP amount, the slippage, return data, and pre-made accounts. And if we return data is true, we also use the instruction data. Now we pass the pre-made accounts here because we want the contract to send token A and token B directly to the user. So why do we withdraw not to the associated token accounts, which we created earlier, but to the arbitrary token accounts, which is the message sender and the user? That's really quite simple. We want the transaction to go directly to the user from Raydium and not through the contract to the user. So each one of the balances stored in PDAs on Solana, they are not associated token accounts, they are arbitrary token accounts. So to send directly to the user, we need to specify these arbitrary token accounts, not ATAs. And if we send to associate token accounts, the tokens won't be lost, but they will arrive in the contract. And that's just a longer path, where you first withdraw tokens from Raydium to the contract, and then you need to withdraw to the user. The easier, cheaper, and smarter path would be to withdraw from Raydium directly to the user, and this is done with the arbitrary token accounts. And another thing, we pass the return data to be true in the instruction buildup, same as we did for create pool and add liquidity instruction, because they all need the return data to be true to be successful. Now let's look at lock liquidity instruction. Here we specify the pool ID, the lock liquidity amount. This can be different from the whole liquidity amount in the pool, because you can decide to lock, for example, only half of it. So in Raydium, when you lock liquidity, you get an NFT, and here is when you can attach its metadata. And this might be useful if you might decide to sell your NFT position. Then we specify salt to calculate the NFT owner. And basically you need salt because there might be multiple NFTs, and if creating a pool requires multiple liquidity provisions at the same time. So later you'll be able to pass the salt and address a specific NFT owner. The next method is collecting fees. Now, collecting fees is only possible after there has already been traffic in the pool, like swaps. And here's where you also pass the salt that's linked to the same NFT position which you got for locking the liquidity. Then we have two types of swaps, swap input and swap output, which is similar to Uniswap. It also supports both types of swaps. Now, you've probably encountered it as a DeFi user yourself. When we use a swap, with swap input, we can specify the exact input amount for a swap, not knowing how much we are going to get in return because it depends on slippage. For example, swap 100 token A for X amount of token B. And vice versa, with swap output, you can specify that you need to get 100 token B for X amount of inputted token A. And the value of X depends on the slippage parameter. Both swap input and swap output point to the same internal method, which is just swap. And that's because they have exactly the same account structure, only different data. So going to the implementation of swap input, here we specify the token mints, the pair account, and the input token ATA, because we need to deposit the tokens A to the ATA account for the swap. So then we move the tokens from the user to the ATA, and then we do the actual instruction generation and execution, passing the instruction to Solana. Swap output is the same, only a reverse instruction of the swap input. Now, I promised you earlier to tell when you need return data to be empty, and this is where you don't want the library to build the instruction data for you. In our example contract, we have this more advanced function called create pool and lock LP, which combines these two instructions, create pool and lock liquidity, in one atomic transaction. And for this instruction, we define the token A and token B, their mint amounts, and also their associate token accounts. For all of this to work, the contract has to have initialized associate token accounts for the tokens that we are willing to create pools for. Then we transfer token A and token B from the user to the associate token accounts of the contract, and now we build the first instruction, which is creation of a pool. Here we say to the contract to basically return data as true. So we pass this as true, and the library builds the data for us. But then the second instruction, you will notice that the second instruction is a semi-building instruction, which means that in a way we say that we want only half instruction to be built, but not all of it. So why are we doing that? And we also return data as false here. So we are going to the locking liquidity method and pass this boolean as false, so that we wouldn't end up getting this into this condition here and data wouldn't be built. So data lock will be empty. Why? Basically because we need first the pool to be created. So we create the pool, and by the time of deploying the pool, we cannot know how much liquidity we will receive after the pool creation. So this is why we create the pool here, and then we request Solana to check how much liquidity balance we received after the pool creation. And only then we build instruction data and attach it to the execution of the second instruction. So you can look at this as two instructions, where the second one is depending heavily on the output of the first one. And this is a very complicated way to create a pool. If you'd like, go ahead and look through it once again. You create a pool and lock liquidity as one atomic transaction, which makes it, of course, more optimized, but at the same time more difficult to understand. And again, this is when we need our return data to be empty, because we will figure out how much liquidity is in the pool only after the fact, only after the first instruction has completed. So I think this is a good way to stop. To sum up, we've seen how to call Solana's high-performance DEX Raydium from our good old Solidity with the Raydium library. And what you saw today, all these instructions, creating a CPMM pool, adding, removing liquidity, Even collecting fees and doing swaps is actually just a tip of an iceberg. You can mix and match these instructions to create entirely new DeFi experiences right from your Solidity code. And if you're feeling bold, go beyond the tutorial, build an advanced contract that locks LP tokens as NFTs, or lets users swap with custom slippage logic. But the actual task for this week is not just to follow along. The task is to come up with your own use case for the Raydium composability library. It will most likely be a DeFi use case, but feel free to get creative and think of something new and absolutely innovative. So here is how you can approach it based on your experience level. If you don't feel very confident in your coding skills, you can run the test script, which you can find in this GitHub repo, to see how a Raydium pool is created and used. Then think of a potential DeFi use case for the functionality you see in the test script, and in your README file describe your idea very clearly, what the dApp would do, how it would use the Raydium instructions, and basically what the idea behind this is. You don't need to create custom logic, just show that you understand what's possible using this library. But if you are an advanced coder, then you can not only come up with a DeFi use case that uses these Raydium instructions, but you can also write your own smart contracts implementing this idea. If you don't have time, you don't have to build a UI. This is totally optional. You can showcase your idea and your work by simply writing and running test scripts, and including the deployment links and the descriptions in the README file that you submit. Thank you so much for your time. I'll see you next week.